Two sample hypothesis tests and ANOVA, Chapter 7, Part 2. So we're going to go over two sample hypothesis tests, difference in means with known sigmas, unknown but equal sigmas, and unknown but unequal sigmas, a difference in means with paired samples, and a test for variances. Some of our tests that we need to do assume equal variances in the population, and so we'll want to do a test for that before we can make that assumption. Then we're going to talk about analysis of variance, or otherwise known as ANOVA, and a chi-squared test for independence. So again, our steps for a hypothesis test are to identify the population parameter of interest and formulate the hypotheses, figure out your level of significance, alpha, use the data to calculate your test statistic and the p-value, and then draw a conclusion by comparing your p-value to the level of significance, alpha. If p is less than or equal to alpha, you're going to reject the null and find in favor of the alternative. And if p is bigger than alpha, you're going to fail to reject the null, do not find for the alternative. So we want to compare two population parameters to some constant. So in our one sample hypothesis test, we compared one population parameter to a constant. Now we're just going to have two. So we're going to use two samples of data, and we're often interested in the difference, that is subtracting the two population parameters. And again, these can be lower one-tailed, upper-tailed, or two-tailed. So for example, do average bolt diameters from two separate suppliers differ? Or does average on-time performance differ at two plants? Steps are similar to those discussed for the one sample test. However, the test statistics in general are more complicated. And so we're going to use Excel's analysis toolpack rather than computing test statistics ourselves, except in the case of the F-test for variances. So the tool will calculate the test statistic, the p-value, and the critical value for both one-tail and two-tail tests. We are not going to use the critical value, even though it gives you the critical value, we're not going to use it. That's a very old-fashioned way to do hypothesis testing. It's much better to report the p-value, so you know how much evidence you have against your null. And we're not going to use the variance test in the toolpack either. We're going to do that one by hand, because the one in the toolpack it doesn't save any time at all. So, and it can be very confusing. So it's going to be much simpler for us to just do that one by hand. And we're going to need to be careful interpreting the results, and you'll see that when we do our examples. All right, so the first order of business is to discuss the hypothesis test for the difference in means with these three situations, either known sigmas, unknown but equal sigmas, or unknown but unequal sigmas. So let's start out looking at a one-tailed hypothesis test. And suppose your research question is the population mean for sample 1 less than the population mean of sample 2? How would we formulate our hypotheses? Well, our research question is that one. The alternative hypothesis is mu1 less than mu2. And that makes our null either mu1 equal to mu2 or mu1 greater than or equal to mu2. Remember, as long as that null gets the equal sign. But another way that we could write that, if mu1 is less than mu2, isn't it true that mu1 minus mu2 would be less than 0? So we can write these hypotheses in a different way. Sometimes I'm going to write them as the way on the left and sometimes as the way on the right. Writing it that way that you have on the right of your screen allows you to make the difference non-zero. So you could investigate whether mu1 minus mu2 equals 5 against the alternative mu1 minus mu2 is less than 5. So that could be any constant, but generally we go with 0 because we're just making a comparison. And we have the same three alternative hypotheses. We've got less than, greater than, or not equal. So we have our three types of tests we're going to look at: known sigmas, unknown but equal sigmas, and unknown but unequal sigmas. But we generally, in practice, don't know the population variance. It's hard to justify why the unknown population variances would be equal. So if we don't know the population variance, this one's generally not going to be used. If it's hard to justify that the population variances are going to be equal, we're generally not going to use that one. So we're most of the time going to go with this one in practice, where you have unknown and unequal sigmas. So That makes it so that in most practical situations, we're going to use the menu option that says to sample t-test, assuming unequal variances. So the t-test is the unknown variance part, and then it says unequal variances. So we're going to do an example to start off with. So we're going to jump over to your Excel spreadsheet. We're going to investigate whether the mean lead time for alum sheeting is greater than the mean lead time for durable products. Okay, so here we are on our in-class examples workbook, and I have it open to this example, tab for 9 and 10. So our research question is, we want to know whether the mean lead time for alum sheeting is bigger than the mean lead time for durable products. So what's our research question then? Our research question is our alternative hypothesis, and that is that mu for alum sheeting, we'll call it 1 because that's the way it's going to be denoted in Excel, is bigger than the mean lead time for durable products. That's our research question. So that's our alternative hypothesis. And what does that make the null? Again, you can either write mu1 equal to mu2 or mu1 less than or equal to mu2. Either way is fine with me. All right, so we've got our hypotheses, and make sure you notice that we could rewrite these as the null hypothesis. If mu1 equals mu2, then mu1 minus mu2 is 0. There's no difference because mu1 equals mu2. And the alternative hypothesis could be rewritten in the same fashion as mu1 minus mu2 is bigger than 0. If mu1 is bigger than mu2, then when you subtract them, you'll get a positive difference. All right, so we need to conduct our hypothesis test. So let's go ahead. Notice that we've already sorted the sheet so that your data, so that the suppliers will be grouped together. So we've got alum sheeting here on the top and durable products next. So we're going to go to your data analysis toolpack, click on the data tab, data analysis, and we're going to find the menu option for this test. So we've got a sample data, unknown variances, population variances, and we're not going to assume that they're equal. So we're going to look for the t-test to sample assuming unequal variances. So there it is. All right, and our variable 1 range has to match what mu1 is. So we said that mu1 was denoting alum sheeting. So I'm going to go ahead and highlight the lead times for alum sheeting for my variable 1 range. And my variable 2 range we said was durable products. So for this one, I'm going to go ahead and highlight the lead times next to durable products. All right. And what's our hypothesized mean difference? Ours is 0. Our null hypothesis was there was no difference. We don't have labels because we don't have these in separate columns, so we're going to leave that unchecked. And I'll just let it pop up the worksheet where, actually I'll put it on here. Let's go ahead and put it in this worksheet since you guys are going to need to see it while we're looking at our p-value. And I guess I'll put it here and just erase what I wrote in a second. So I'm going to go ahead and click OK. And it's putting the output there. All right, now let's see if I can get rid of that. There we go. Okay, so I'm going to just go ahead and write the null and alternative hypothesis down again real quick since I had to erase all of it. mu1 equal to mu2, and the alternative mu1 bigger than mu2. All right, now we're cooking. So we have our output here. So we've got lots of stuff in the output. We've got the means for each sample, the variances, the number of observations in each sample, the null hypothesized belief of what the mean difference is, and the degrees of freedom for the test. So notice that we didn't give you the degrees of freedom, how to calculate the degrees of freedom for the test, That's because usually you won't get a whole number for this type of test, so we're going to let Excel calculate those for us. We've got our test statistic here, which is 3.82796. So if I draw a picture of my test, okay, so let's just draw our t-distribution here. How are we calculating that p-value? Well, there's my t-distribution, and I want to plunk down my test statistic, so 3.83. So it's way up here in the right tail. How do you get your p-value? Well, since our alternative is greater than, my p-value is the area to the right? So what I'm going to suggest that you do, because Excel does something really weird with the one-tailed tests, it might not necessarily match the direction of your test, because notice it didn't prompt us to feed it an alternative hypothesis. What I'm going to suggest you do is always look at the p-value for the two-tailed test and decide whether to cut it in half or do another trick, which we're going to find in another example. So what is Excel calculating for the p-value for the two-tailed test? It calculated the area above positive 3.83 and the area below negative 3.83. So once you know that that's the picture where the two-tailed t-test came from, the two-tailed p-value came from, then you can clearly see that our area is just 1/2 of that two-tailed p-test p-value. So that's 1/2 of 0.0033. Okay, and we're going to play that game every time we use this output when we have a one-tailed test. I think it's easier to keep track of, and you'll have less room for error, making mistakes. And this is often the way the output comes out of lots of other statistical packages anyways, so it won't hurt us to use it. So our p-value is 1/2 of this p-value. So it's this one cut in half, divided by 2. And it's rounding it to essentially 0 here. It should be like 0.0015, depending on how you have your rounding set in your cells. What's our decision? Well, clearly my p is less than my alpha, right? So what do I do when my p is less than my alpha? If the p is low, the null must go. So we're going to say to reject the null hypothesis. And what's our conclusion? Our conclusion is there is significant evidence. So if we rejected the null, there is significant evidence for the alternative. There is significant evidence to conclude, I suppose I should say what level, at the 5% level, to conclude mean lead time for alum products is greater than the mean lead time for durable products. And there you have it. You've done your first 2 sample tests. So now we're going to suppose the reverse is true. We're going to suppose that we want to find out if the mean lead time is greater for durable products. So I'm going to switch back to your slides to handle this example, and we'll write it in there. Okay, so another way that we can write this question down, if we want to know if the mean lead time for durable products is actually greater than the mean lead time for alum products, is to ask, is the mean lead time for alum products less than the mean lead time for durable products? So let's investigate how we would get the p-value for this situation. So let's first write down the hypotheses. What's the null hypothesis? That's that there is no difference. Mu1 equals mu2. And our alternative hypothesis this time is that mu1 is less than mu2, right? We want to know if alum sheeting is less than durable products. All right, so let's draw our picture. We fed our sample 1 and our sample 2 into our statistical software, and it calculated our test statistic, right? It has the test statistic as 3.83. But this time, our alternative hypothesis is less than. So what's our p-value? It's going to be the area to the left of the test statistic. So our p-value is going to be really, 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 really big. So not only did our data go in the opposite direction of what we thought was going to happen in our research hypothesis, it went really, really far in the opposite direction. Okay, so how do I get my p-value from my two-tailed output? Well, remember what Excel was calculating for this two-tailed p-value was the area to the right of positive 3.83 and the area to the left of negative 3.83. Now, from this picture, we can get our p-value that we need from our picture. What do we need? We need the total area to the left of 3.83. So we can calculate that. There's half of the 0.0033 in this tail and the other half down in this tail. So what's this area that we need? It's 1 minus this upper tail area. So the p-value for this one is 1 minus 1/2 of the two-sided p-value. So this is why I was telling you it's always important to draw a picture until you get really accustomed to doing these hypothesis tests. Notice that Excel doesn't know that we have a less than alternative hypothesis. It still reports that upper tail area in this case as the probability of being less than or equal to a t. So their notation is not good. That tail area, I think, goes in the direction of your test statistic, not of your alternative hypothesis. And it's important that we keep track that it's supposed to go in the direction of our alternative hypothesis. Okay, so that's that example. So now let's do an example with paired samples. So those examples were with independent samples, where we have completely separate samples from completely separate suppliers. In some situations, data from two samples are naturally paired or matched. For example, assembly line workers can perform a task using two different types of assembly methods. Which type is faster? Paired data one plausible scenario for paired data would be having 50 workers perform the task using each of the two assembly methods. So each of the 50 workers would have 2 data points associated. To do it in the independent sample setting, we could just have 50 workers perform the task using the first method and another different 50 workers use the second method. When paired samples are used, a paired t-test is more accurate than assuming that the data come from independent populations. So forms of the test, again, we can look at our mu-d, that's the mean difference, as being less than, greater than, or not equal. So we can have all 3 of our same alternative hypotheses. All right, so note that you must have the same number of observations for each of the 2 samples. If any of your pairs is missing its pair, then you need to exclude that one from the calculations. So let's go ahead and do an example of a paired 2-sample test for means. All right, we're going to do this pile foundation example. A contractor wants to know if there is a significant difference in the means of estimated and actual pile lengths. So let's jump over to our Excel workbook sheet to do this example. So our investigator wanted to know whether there was a mean difference in the estimated versus the actual pile length. So first, let's write down our null and alternative hypothesis. So we'll write it over here. So our null hypothesis is what? That mu-d is 0. There's no difference. And the alternative, the investigator didn't specify a direction, so it's going to be that mu-d does not equal 0. All right, so we've got our null and alternative hypothesis set up. Now we need to go ahead and calculate our test statistic and p-value. So let's click on the Data tab, go to Data Analysis, go to the t-test unpaired to sample for means, and click OK. And then we've got our data in these separate columns. So I'm just going to highlight the estimated, as my first sample. Control Shift down. I'm going to highlight my column name too. Oop, my computer's acting up. There we go. All right, so it goes down to 315. So I'll make a note of that for this next one. And my actuals will go from C4 through C315. There we go. And my hypothesized mean difference is 0. I did include my labels this time. And I'm going to put my output right here in this same sheet. Oops. Okay. I'm going to go ahead and put my output in the same sheet. There we go. Whew. And click OK. All right, so there is my output. And I'm just going to, I overwrote my little blank spaces here. So I'm going to type those back in. All right, so let's figure out what we're doing here. So we need to get our p-value from this. Well, this is a not equal to alternative hypothesis. And so you can just directly grab what Excel calls your two-tailed p-value. So you can just directly grab that. So our p-value is really, really tiny. This 1.119e minus 23 stands for 1.1 times 10 to the negative 23rd. So we'd have 22 zeros after the decimal place before we got to a 1. So in practice, the way that we would typically report that is that p is less than 0.001. That means that's our way of saying it's really, really tiny. All right. Our decision then is obviously p is less than alpha, right? So p is low, then all must go. And then we can write our conclusion. So what's our conclusion? Well, if our p is less than our alpha, is there or is there not significant evidence for the alternative? There is. If we reject the null, there is significant evidence at the 5% level to conclude the mean difference is not 0. Or that there is a difference in the means of the estimated versus the actual, what was it, pile lengths. All right, and that's that. So we'll jump back to our slides to finish up this chapter.